Yeah, good morning, all of you. I want to introduce myself. I'm Sanat Kumar. I have 16 years of experience as a VLSI trainer and industry. I have experience. Presently, working as a trainer in Gnanodaya VLSI. Today, I want to share some. I want to give some exposure in the VLSI. What are the job opportunities in VLSI and VLSI in the VLSI? What are the roles are there in the VLSI that I want to discuss about today's session. So thank you for giving me the opportunity to deliver my lecture. Yeah. So these are the contents I'm going to deliver, VLSI semiconductor industry and physical design flow, ASIC design flow, design verification, analog layout. AMS is nothing but analog and mixed signal and custom IC layout, ASIC and chip design flow. And so I want to introduce about Gnanodaya VLSI technologies and our placement process and VLSI and semiconductor. What are the companies are there all over the India? Mainly categories of the VLSI companies, eligibility criteria to get into this VLSI course and training methodology, and AMS and customized design flow, ASIC or chip design flow, and any queries, any doubts or queries, you can ask me after completion of this session. Okay. Hope my voice is clear so that I will move forward. Please, anyone confirm me.
Yeah.
Okay, okay, thank you. Okay, yeah. So basically, VLSI or semiconductor industry, if you see, so basically, semiconductor companies are broadly classified into mainly three parts. One is product-based companies. Okay, so product-based companies are nothing but the companies which will manufacture their own ICs, like yeah, Intel will make their own ICs, processors, AMD, okay, Qualcomm, Nvidia, okay, Samsung, okay. So those will produce their own ICs. Those are nothing but product-based companies, okay. Service-based companies are nothing but they will not produce any product. They will give the service to these product-based companies as well as EDA companies, okay. So there are some service-based companies are there all over the India. There are so many service-based companies are there. Okay, and EDA companies. EDA companies means EDA is nothing but electronic design automation. Okay, so you already studied about that is SSI. Okay, small scale integration, MSI, medium scale integration, LSI, large scale integration, VLSI, very large scale integration, and ULSI. Okay, ULSI, ultra large scale integration, and GLSI, giant scale integration. Okay, so small scale integration means some you have like 10 gates are there. Okay, some thousand transistors are like that. You can implement the gates manually. You can design. Okay, medium scale integration means you are designing some combinational or sequential circuits. Okay, LSI is nothing but you are designing some system level RAM, ROM like that. Okay, VLSI is nothing but you are designing a system or system on chip. Okay, so what happens? So there is a Moore's law. So Moore's law given a statement that the number of transistor count doubles for every 2 years. Okay, every 18 to 24 months, every 2 years. So now itself it's satisfying. So we are working under like 3 nanometer technology. Okay, now we are in 3 nanometer. So where they are developing on 2 nanometer technology also. Okay, so what is this technology? Technology is nothing but you already studied about MOSFET. The MOSFET, the distance between the drain and source, that is a channel. Okay, channel. This channel length is nothing but we call as a technology. Okay, so some 100 crores of transit. VLSI is nothing but 100 crores of transistors are there. Some millions of transistors are fabricated with an IC. So manually designing this IC is not. It will time taking and manually it's impossible. Okay, so we need to take the help of EDA tools. Okay, so EDA tools are like that. Like in VLSI front end, you have some EDA tools, and VLSI back end, you have some EDA tools. So these EDA companies, they will produce their tools. They will develop the tools like Cadence, Mentor Graphics, and Synopsys. Okay, so with the help of this EDA tools, we can design the so like in Cadence you have Xilium, and in the front end you have Xilium, and in a static timing analysis you have prime time, and in back end you have Cadence Innovus tools for physical design. For the mental graphics also, for the front end you have model sim, QuestaSim, and for synopsis also you have VCS compiler. Okay, all those different names are there for both the front end and back end. They will develop the these tools. With the help of tools we can design. Okay, so what is ADA product and service based companies will always synchronize up. Okay, they will always combine. Okay, they will always combine to meet the technology deliverable with the support of what VLSI engineers. Okay, so we need the VLSI engineers. Okay, so this is about the difference between the product based companies, service based companies, and EDA companies. Okay, so wherever you say that VLSI companies are divided into this three categories only. Okay, and coming to physical design flow, before that I want to say about this total ASIC design flow. Basically, like in VLSI, mostly the target devices are ASIC, and FPGA. ASIC is nothing but application specific integrated circuit. Application specific integrated circuit means they are manufacturing their IC for only for specific application. Suppose like when you are making your IC for your computer, okay, that IC only for your laptop only, okay, or only for your desktop only, or your household application. Suppose washing machine, air conditioner, or uh, like a microwave oven. Okay, so you can't use that IC whichever you are using in the washing machine. You can't use in your ACs. Okay, in automobiles also, like different ICs are used for different auto lock braking system or engine control system, airbags. Okay, so that means that IC mainly manufactured. They are producing for the bulk production. Once the program is written, we can't change in this ASIC. Okay, so that is nothing but ASIC, and FPGA is nothing but we can reprogram. Suppose if you wrote the code for some RAM, okay, from some RAM, you wrote the code. After that, if you want to write the code for sequence detector using FSM, okay, so you can write the code, and that whatever the code is there, that will be erased. It consists of some lookup tables, lookup tables. In this lookup tables, the circuit will be formed. Okay, CLBs are there, configurable logic blocks, IO blocks, and inside there will be a mux will be there. Okay, so this is means configurable. Configurable means we can use for R&D purpose. Okay, so these are the main target devices. So mainly this is ASIC design flow. So ASIC design flow, if you take design specification means, suppose any IC, if you want to make, so over the architectures are there, they will make the specification, how much power it will take, how much area it will take, how many input and output lines it have. Okay, and next, that IC is for which application, means it is that is implemented for computer application and networking or security purpose. Okay, so that whole thing will be decided in the design specification. In the VLSI, some architectural engineers are there. Those having around 25 to 30 years experience, they will take the specifications from the client, and they will make these architectural specifications. Okay, and after that, you need to go for architecture means, suppose CPU you want to architecture. Okay, you need to do. So in CPU, what will be there? Just example I am telling. In CPU, what will be there? You have ALU, and memory unit, control unit, and bus interface unit. Okay, so that means where the ALU should be placed where the memory unit should be placed. That total planning. Okay, that planning you already studied about the computer architecture. Okay, so how the inside how the modules will be there, all like that. So if you want to design any IC inside, you need to do the total like architecture is nothing but we can call as a blueprint. Okay, so we can make this architecture. Okay, and after that you need to do the micro architecture. Micro architecture means sub modules. So that means in CPU, what are the sub modules you need to design for architecture for ALU, you need to do the architecture for MU. Memory unit means again you need to design for RAM and ROM. Okay, and suppose flash also. Okay, and control unit, bus interface unit, all those sub modules architecture is nothing but micro architecture. Okay, and next coming to the, so after my architecture and micro architecture, RTL design will come into picture. RTL design, RTL is nothing but register transfer level. Register transfer level. Okay, so that means you need to write. That means basically like in the programming language, there are two types are there: high level language and HDL. High level language means you have C, C++, Java, Python, those are there, no? So they will not produce any hardware. They will develop the application only. But HDLs will develop the hardware. So in HDLs, you have Verilog and VHDL. Okay, Verilog and VHDL. So basically, like for the ASIC, we are using Verilog only. So Verilog will follow C syntax and some different types of modeling styles are there, like switch level modeling, data flow, gate level modeling, data flow, and behavioral modeling. So that means mainly in RTL design, we are using data flow and behavioral modeling only. Okay, that can be synthesizable. That means we can convert this one into hardware. Okay, so for this purpose, you need RTL engineers. You need a RTL engineers. Okay, and after that, you are using Verilog means up to some modules like FIFO or RAM. Okay, we can write the Verilog code and we can verify the functionality of the circuit by using test bench. But when you are going for the complex circuits like SOC, system on chip, or intellectual properties, IPs. Okay, so complex circuits we can't go for the we can't use the Verilog for the verification. So we need to use for other languages like SV and UVM. Okay, system Verilog and UVM. System Verilog means some more properties we added in the compared to Verilog, like two level data type and some more like polymorphism, like oops concept will come into the picture. Okay, and we can write the test bench by using SV and UVM, like SV is robust. That means we need to, suppose if you write the test bench for I2C, separately need to write for SPI. Okay, so there is no just means everywhere everything you need to write in spreadsheet. Okay, so what the companies have gone, they want to UVM. UVM is nothing but universal verification methodologies. Okay, this is not a language. This is nothing but methodology. Suppose you wrote the test bench for SPA. Some modifications, same test bench you can, with some modification, same test bench you can write for I2C. Okay, this verification will be done by this verification engineers. Okay, RTL verification engineers. They are also called as DV engineers. Okay, DV engineers. Okay, so these both will work together. Okay, first architectural engineer and next RTL engineer and verification DV engineers. Okay, these two work together. So RTL engineers will design whatever the specification is there, and next verification engineers will verify with the test bench whether this design is meeting the specifications, are that meeting this functionality or not. Okay, So this is about the design and verification. So if design is met, again it will go to the next step, and design is not met, again it will go to the RTL design. Okay. So in the so there is a logic synthesis is there. So logic synthesis is nothing but after RTL design and verification, there is unoptimized netlist will be generated. Netlist is nothing but gate level netlist. Gate level netlist, unoptimized gate level netlist with some simulations. Okay. So in the synthesis, you need to do for the constraints. Those what are the constraints means area, time, and power. Okay, so that means it should be whatever the IC you are means making, that should take less area, and it should be high speed. Okay, okay, less delay should be there, and it should take low power. Okay, so whatever these constraints, they are working under these constraints. Okay, and after that, there is DFT. DFT is nothing but design for testability. Design for, so for this you need synthesis engineers, and design for testability. Testability, you have DFT engineers also. So DFT engineers, what they will do means, so they will test your design whether your design is meeting the functionality or not, with some what we call fault cases, stuck at faults, built-in self-test, okay, MBIST, and all those things. They will test your circuit. Okay, there will be ATE, automatic test equipment. Okay, so already some predefined test cases are there. So those are matching means your IC can be work properly. Okay, those are not matching means again the IC will be defaulted IC. So this is nothing but testing. Okay, and LEC is nothing but logic equivalency check. So logically they will check whether this is meeting the functionality or not. Okay, and coming to STA, okay, STA is nothing but static timing analysis. Static timing analysis. There is pre-layout STA, and after physical design, there is post-layout STA. So pre-layout STA means they will work under the delays. Okay, suppose in digital you already studied like this is AND gate. So you are getting the output y equal to AB with 0 time units. Okay, 0 nanoseconds. Okay, this is ideal case, but practically it will be not there. There will be some propagation delay for this gate. Okay, uh, they will make with some setup time, hold time, setup time violations, hold time violations, and they will do some maximum timing analysis for the setup time violations, and minimum timing analysis for hold time violations. Okay, so for this STA means with respect to delays, they will work on the that. So we need STA engineers, STA engineers. Okay, and next you have PD flow. Okay, what is this PD flow means physical design. Okay, so that means here till synthesis you will get the front end. Okay, VLSI front end. Physical design, this is physical design, VLSI physical design. Okay, so physical design I will tell you in deep, like what is physical design means. In physical design you have partitioning, floor planning, power planning, placement, clock tree synthesis, routing, and timing closure. Okay, these are there in the physical design. That means they will take the, so till here like there is a front end, VLSI front end, VLSI front end. Okay, back end will be, they will, this PD engineers, they will take the input from the front front end, whatever the inputs coming from the front end, and they will like they will design the your IC. Suppose like example, if I say, suppose if you are like constructing any building, first you will make some basements, no? So like that you need to do floor planning. After that you need to construct the walls, and next you need to make the electrical connections. Okay, that is power planning. Okay, and placement same like that. They are making the IC, the speed engineers. Okay, so this is the physical design engineers, PD engineers. Okay, so you have PD engineers. Okay, you have PD engineers. And parasitic extraction means when they are designing between the two metals, there will be small gap. Okay, there is the minute gap will be there. So for the metals you are mainly you are using copper. There will be some RC extractions will be done in the parasitic extraction. Okay. There will be some resistance and capacitance for the metals, no? So that RC extractions will be done in the parasitic. And after PD and parasitic extraction, there is a post layout STA. Okay, so ST is there in the preload and post layout. Okay, if design is met, again it will go to the next step. If design is not met, again they will go to the PD flow. Okay, physical verification means they will check. So verification is there in the front end as well as verification is there in the back end. So they will check for like antenna checks, EM checks, all those verifications will be done. And after that, at last, there will be a GDS2 file, a graphical database system. GDS2 file will be given to fabrication. Fabrication, they will do the fabrication based on the CMOS fabrication like NMOS technique, like twin tube process or N-well process. So many techniques are there. Some oxidation, and implantation. Okay, so many are there in the fabrication. So they'll make the IC. Okay, so mainly for the like in the ASIC design flow, you need like 10 to 15 engineers are required for each and every area. Okay, so you need RTL engineers, verification engineers in the front end, synthesis engineers, DFT engineers, STA engineers, PD engineers. Okay, and post layout STA engineers, PV engineers. Okay, fabrication also layout. Basically, the VLSI is divided into two parts. One is analog and digital. So this is basically digital. At last, they will combine this analog and digital both together. Okay. Hope you understood this ASIC design flow. And so physical design means I told you physical design means mainly first it will come for the floor planning. Okay. So in floor planning, you are planning your floor how the die will be there. Okay, at last you are making a pure silicon die. It will be like a cd type structure. Okay, so you need to do the so you need to fabricate all the uh, modules in the die itself. Okay, so you need to estimate the die size, the IO and macro placement, and planning power distribution. All those things will be done in the floor planning. Okay. So what are the goals of the floor planning means all the macros should be placed in the grid, no overlap in the macros. Okay, there is no DRC, design rule checks, or layout versus schematic violations. Okay, minimum conjunction, and make sure the design timing is meeting. Okay, these are the main goals of the floor planning. Okay, and what are the input for the PD means physical design means one is .v file. As I told you know, like synthesis. What is synthesis? Synthesis is nothing but you are converting your code into gate level netlist. Gate level netlist. Gate level netlist that to optimized gate level netlist. Okay, that is coming from the synthesis. Output of the synthesis is gate level netlist. That is nothing but .v file. Okay, and some constraints I told you know, ATP, area, time and power, that too coming from the synthesis. And logical library files means some analog blocks are there like IO blocks or PLLs. Okay, some IO blocks that will be there in the logical library file. Okay, physical library file. Okay, multi voltage domain UDF files. These all inputs will be taken by the PD, so as a input to the PD. Okay, physical design. So floor planning goals I told you know. So you need to estimate the die size. Okay. So this is the this is core area total. This is core area. How the macros are placing in this your chip. and this is IO area, total corners IO area. Okay, so planning for IO parts, so power planning, and all those things will be done in the floor planning. IO planning means uh, uh, so we can receive the three different types of input from FE regarding IO ports, like you are getting from the decoder, a latch or buffer. Okay, so you need to do as a IO related IO planning. Mm, Floor planning elements. What are the floor planning elements? Means uh, there is a core area and die area. Okay, core area is nothing but where the standard cells or macro cells are placed. Standard cells are nothing but already those are available in terms of gates, okay, like NAND gate, NOR, okay, NOR, or flip flops, okay, in types of, that means already predefined, pre-designed terms we call as standard cell. Okay, so this is nothing but total core area, and this total part is nothing but die area. Okay, so die area is nothing but it includes the total core area as well as total die area. Okay, so placements means what is placement means this is giving the exact location in core area to the standard cells is called placement. Okay, so it gives the exact location. Okay, so what are the goals means it will less utilization of gems, no conjunction, no overlaps, good timing values. Okay, these are the placement goals. So when you are taking the physical design, you are going to study about each and everything in detail. Just I am giving some idea about what are those. Okay, clock tree synthesis is nothing but there will be one global clock. Different modules are there in your IC, no? So that means there is a clock distribution. That means all ICs will not operate with same clock, no? So inside where there will be a clock dividers, or inside there can be PLLs. Okay, so that we can multiply the clock or we can divide the clock depending on the clock requirement. Okay, that will come under the clock tree synthesis. Clock tree synthesis. Okay, and routing is nothing but connections. How we are doing the connections with different macros and standard cells. That comes under the routing. Okay, this involves global track roads. Okay, connections are made between the signal pins and metal layers. There are some different metal layers, metal one, metal two, like that. Different metals are there, no? So we need to connect with the help of the tool only. We can do this routing. Okay, and verification I told you, no? So verification means you need to, after physical design, you need to verify electrically, or you need to verify physical verification. And so in electrical you need to check for power estimation, IR drop, power EM, signal EM, all those things you need to verify. And layout versus schematic design rule checks. There's some, like when you are drawing the stick diagram for CMOS circuit, there should be some design rules. Okay, that you need to follow. Okay, that comes under the design rule checks. Okay, suppose for VCC there will be some dimensions. Okay, for polysilicon, or for gate, for substrate. Okay, all those things you have some dimensions that you need to follow in the design rule checks. Antenna checks also. Okay, crosstalk, you need to check for crosstalk. Okay, so after all this, this only you need to go for tape out. Okay, verification is there in the back end also. For that we need PV engineers. So this is about the physical design. Okay, so this physical design you are going to study when you are taking the physical design course. This is front end physical design and verification in VLSI. So physical design and verification means, so if you take VLSI, wherever you see VLSI is there. Suppose microprocessor or computer, okay, graphic cards, digital camera, okay, cam cards, cell phones, okay, embedded process, wherever anti-lock braking system, okay, automobiles, okay, in automobiles, personal entertainment system, okay. Nowadays you are getting augmented reality, all those entertainment related everywhere from day one onwards you are seeing the VLSI. Okay, so you already studied about microcontroller, microprocessor, and this is nothing but SOC. What is this? System on chip. system on chip. Okay, system on chip, that I will tell you. And FPGA. FPGA means, already I told, field programmable gate array. Okay, field programmable gate array. So microcontroller is nothing but, suppose, so you want like, it is nothing but within an IC, you have CPU, ROM, RAM, timer, serial IO ports, serial interface. Serial interface means UART or IO ports within an IC. Okay, example like 8051 microcontroller is there. It's a 40 pin IC. You already studied about this in microprocessor or microcontroller or embedded devices. So what is the purpose of this microcontroller means, this will do a specific task. Okay, if we want to do some specific operation, then you can, mainly these microcontrollers we are using in the embedded systems. Okay, uh, so how much of clock rate it will be operated at 1 megahertz to 300 megahertz. It consists of some synchronous communication protocols also, I2C, inter-IC communication, universal asynchronous receiver and transmitter, SPI, serial peripheral interface. Okay, these are some protocols inside, how to communicate between the different modules. Okay, so this is about the microcontroller. Microprocessor means, this is a general purpose processor. I think you already studied about 8086 microprocessor. Okay, 20-bit address line, 16-bit data lines, and it consists of ALU, some register array. Okay, so many registers are there, control unit. Okay, so ALU performs some multiple different arithmetic and logical operation. So it will be operated at a more frequency. More frequency means, from 1 to 4 gigahertz it will be operated. Okay, and coming to the system on chip, this is nothing but, we can call components on one piece of silicon. Okay, something like in embedded also, you have Raspberry Pi. Raspberry Pi is also one system on chip. Okay, and you have Ryzen 7, Ryzen 5, Intel i5, i7 processor. That is nothing but we can call as a system on chip. Okay, so why we are using this system on chip means, it will, that means it will eliminating the need of separate or large system components. Okay, no need to interface all those components to the processor or a controller. So we can fabricate all the whatever the components we require within an IC, that we call as a system on chip, or system on, we can call a system on process, system on chip. Okay, so why we are doing means, we can increase, we can means we can work on low power, high speed. Okay, nowadays so many requirements are coming like IoT, augmented reality. Okay, like based on that application, that is depends on VLSI only. Okay, like AI, artificial intelligence is coming. So that means we need to make some graphical ICs also. Okay, so like that. Okay, so that is nothing but system on chip. Okay, you have data processing, embedded memory, graphical GPUs. These are nothing but GPUs. Okay, graphical processing units for gaming purpose. Okay, USB interface, video and audio processing. Okay, so all these are there. You have ARM processor, advanced expansion processor, JTAG, voltage regulator, PLL oscillator. Okay, all those peripherals, Ethernet, USART, SPI for the communication purpose. Okay, ADC. Okay, CAN, USB, PWM, all those things are there. This is nothing but system on chip. Okay, FPGA means, I told you, like suppose this is configurable. Okay, we can like for R&D purpose we can use FPGA. Okay, R&D purpose we can use FPGA. Okay, suppose like suppose I'll tell you one example. You have cell towers. So previously you have 2G, 3G, 4G, and 5G. Okay, now we are operating at 5G. Okay, so so when you are using ASIC in the cell towers, every some 3 years, the communication technology is changing. We can't replace our equipment now. So there we are using FPGA. That means when we'll make the changes in the programming, so that depending on the application, we can load the program into the that cell towers, so that that the cell towers will be operated at this 5G technology. Okay. Similarly, in the defense also. Okay. Technology is changing. Defense also FPGA is used. When technology is changing, okay, they can't purchase these automated weapons. No, those are very costly. So when they are using FPGA, when technology is changing, depending on the technology, they can load the program so that they can make this FPGA. Okay. So I told you it consists of configurable logic blocks. In a configurable logic blocks, you have lookup tables and mux will be there. Okay. So and IO blocks will be there, and this is nothing but programmable interconnects. Okay. Suppose if you want to write the RAM program, you can write the program in Verilog or VHDL, and you can port into the FPGA, and so this FPGA will work as RAM. Okay, so basically internally it consists of some SRAM. Okay, this is volatile. When power is cut down, whatever the program is there, that will be erased. Okay, so again, if you want to write for FSM, you can write the Verilog code or VHDL, and you can port into the FPGA. This will be act as a sequence detector or serial adder like that. Okay, this is about FPGA. This I already told the VLSI design flow, same as previous. As I told you, like what are the VLSI target devices, FPGA and ASIC. Okay, ASIC stands for application specific integrated circuits. Okay, especially for specific application. Okay, suppose like ASIC means previously one person he is using 3G mobile. Okay, nowadays all are using 5G mobile only. Okay, he is not getting any signal. Okay, so he will come to the shopkeeper telling that he is not getting any signal. So based on the demand only, the communication providers will provide the signal, no? So he can't use this 3G mobile as a 5G. Why? Because this is designed only for the 3G only. Okay, so he need to upgrade to 5G mobile. You need to get the speed. Okay, like that. So this is nothing but we can call as ASIC. Your mobile is also one ASIC. In future you are getting 6G, okay, or 7G. Okay, you need to upgrade, or you can change your SIM. So your mobile should support this speed. Okay, so otherwise you need to upgrade your mobile. That means whatever the mobile now you are using, that is nothing but supporting the 5G speed. That means ASIC only. Okay, we can't, once the program is written, we can't change. Okay, so this is improved speed, and this will be produced in bulk level. Once the program is written, we can't change. FPGA is nothing but field programmable gate array, so we can reprogram. Mainly in the R&D purpose, for the R&D purpose, we can use FPGA. Mainly in the defense, we are using FPGA. Okay, in the cell towers. Okay, where the equipment is more costly, we can't purchase there. Depending on the technology changes, we can use this FPGA. Okay, so it is a complex digital circuits. Okay, basically it consists of lookup tables and configurable logic blocks. This is mainly target users of these only, ASIC and FPGA. So this is Xilinx Vivado tool. Okay, Vivado, basically AMD Xilinx Vivado. So mostly what you are doing means HDL. HDL is nothing but hardware descriptive language. So in digital, you already studied about combinational circuits, sequential circuits, FSMs. Okay, the design you already studied, but HDLs are nothing but you are describing your hardware in terms of textual form is nothing but HDL. So there are two types are there, Verilog and VHDL. That I will tell you difference. Okay. So you will write the program in Verilog and VHDL. After that, I told you, know. So this program will be converted into hardware. Okay, by a process called synthesis. Okay, so synthesis will convert into gate level netlist. Okay, that is nothing but schematic. We call as a code into schematic. That is netlist. Vivado tool convert your HDL code into schematic. Okay, after that, what you need to do? You need to do the implementation. Okay, so you need to translate, you need to map, you need to place, and you need to route. Okay, So that will be done in the implementation based on the FPGA board only. Okay, FPGA mode only. So which board you are using, that you need to map, you need to translate, okay, you need to place and routing. All these things will be done in the implementation. And after that, you will generate the bit stream. Okay, that it will be generate the bit stream. It's like a hex file only. Okay, in the embedded also. At last, if you want to develop any application, you are writing the program in assembly language, and for the LCD or 7 segment or stepper motor or DC motor, you are generating the hex file. No, here also you are generating the hex file, that is a bit stream that you are loading into the FPGA. Okay, so this is basically FPGA design flow. So basically, like design techniques, what you are doing, what you are using means functional closure. So how you are verifying this circuit is correct or not, or working properly based on your requirement means you need to do simulation. Okay, simulation. By using simulation, we can, by using waveforms, you can check whether your circuit is working properly or not. That is functional closure. Okay, power closure means proper timing closure or power efficiency, how much power it is taking, like that. You can see in the power closure. Timing closure means, as I told you, know, we need to use static timing analysis and CDC. CDC is nothing but, in digital you are studying about only one clock. That is nothing but single clock domain. Okay. In some designs, suppose if you consider asynchronous before, you have two clocks. Okay. You have two clocks. So when you are studying the design with respect to which is having the multiple clocks, more than one clock, that is nothing but CDC, clock domain crossing. Okay, so when you are operating, that means one design. So one design is operating at one clock, another design is operating at other clock. So when you are communicating with these two designs, so many issues will come, like setup time, hold time, okay, metastability, okay, that you are going to study in the CDC, clock domain crossing. Reset is also very much important in the front end. Okay, so basically when we are using asynchronous active low reset, okay, that is nothing but reset domain crossing. Okay, so before circuit starts, you need to give the reset. That is very much important. Okay, that too, you have synchronous reset, asynchronous reset. Again, you have synchronous, you have active low reset, active high reset. Asynchronous also, active low and active high resets are there. Okay, so basically, like course overview, if you take in the RTL design, we will teach the basic digital electronics. This is the basic for the front end. Okay, so it should be strong in the digital, and we'll teach the Verilog, and we'll give some Verilog project. We'll teach HTA, clock domain crossing, reset domain crossing, and linting will teach. Okay, RTL design and FPGA design. RTL and FPGA design will have the course. Okay, and if it is ASIC SOC verification, we'll teach digital Verilog and Verilog project. HTA will teach. Okay, and system Verilog SV will teach, and system Verilog assertions will teach, and universal verification methodologies will teach. Okay, this is a verification, ASIC SOC verification or design verification also. Okay, this is the course overview. So basically, in the front end, you have RTL design, RTL and FPGA design. Okay, RTL and FPGA design, and ASIC SOC verification. ASIC SOC verification. So, so as I told you, like Verilog and VHDL. So Verilog, VHDL is nothing but very high speed integrated circuit hardware descriptive language. Okay, so this will be like means got universal during 1999 old language. Okay, there will be an IEEE, so they will make this as a universal. This came during 2001. If you see the mainly this is wherever for the ASIC we use Verilog only. High level HDL, easy syntax, easy to learn, and multi-level abstraction. 4 levels of abstractions are there. Okay. Suppose if you compare this Verilog and VHDL, simple example I take. This is AND gate. Okay, you know that y equal to a and b. This you studied in the digital. So when you write the code for Verilog, it will start from any program will start with the module and end module. So this is module and this is module name or identifier. Okay, and I need to declare the inputs, input a comma b, output y, and I need to use a predefined statement, that is continuous assignment statement. Okay, continuous assignment statement. This I am writing in terms of data flow modeling. Flow modeling means I am writing in terms of expressions. When I am writing in terms of expression, that is nothing but data flow modeling. Y equal to a and b, this is nothing but bitwise operator, bitwise and operator. End module. So how many lines are there? Three. Within 3 lines, the code is completed. Okay. If you take VHDL, hard syntax is there. Mainly this VHDL used in defense or academics they are using. Okay, so it will start controlled language, hard to learn, and multi-level abstraction is there. So first, it will start from the header file library IEEE. Use IEEE.std underscore logic 1164.all entity and underscore gate. This is entity name. Port. You need to declare the input and output. A in std logic, B in std logic, Y out of std logic, end and gate. In entity, you are declaring the inputs and outputs. In the architecture you are writing the code. Okay, so architecture of AND gate is begin y equal to, so a and b end architecture. So total, like, it will take 12 lines of code. Here this is easy, within 3 lines of code simple AND gate program is completed, but it is taking 12 lines of code. Okay, so this is universal. Wherever you go, you are using Verilog only for the designing purpose. In the ASIC, they are using Verilog only. Some FPGA design, they are using VHDL. Okay, so both, like, if you know the mm, syntax and semantics. Okay, so if you know the syntax and semantics are very low, you can easily understand the VHDL. Okay, that is not a big deal. Okay, yeah. So this is analog layout. I told you, VLSI is divided into two parts. One is analog, digital. So till now we what we discussed means a digital. Okay, now analog layout. Analog people will do the analog layout like floor planning, placement, routing, DRC, LVS, post layout simulation, and tape out. All those things will be done in the analog layout. Okay, so this is floor planning, placement. Basically, they will design in terms of stick diagrams only. So this is basic CMOS circuit. This is schematic. They will do the layouts. Okay, layouts with some conditions. Okay, design rules. Okay, placement, DRC, design rule checks. Okay, all those things will be, you will study about analog layout. Okay, routing, connections. Okay, DRC. So common errors you need to check. So in the tool only you are using analog. Okay. So in analog layout concept, you are studying about CMOS fabrication, electromigration, IR drop, antenna effects, crosstalk, deep well, latch up, well proximity, HTA, short channel effects, LOD, standard cell, memory layout, analog layout. So for analog layouts or PD, you need to strong in the CMOS or MOSFET, and basic electronics like PN junction, semiconductor physics. So you should be deeply, you need to understand these analog part. These are the basic part. Okay. Suppose if you are when you are going for front end, you should be strong in digital. Should be strong in the digital electronics. Okay. Analog and mixed signal means both. It will combinely analog and digital. That is nothing but analog and mixed signal. Okay. So this is the flow of analog and mixed signal. Okay, schematic design, simulation, and after simulation you will do this placement, routing, design rule checks, LVS, parasitic extraction, LD extraction, post layout netlist. All those things will be done in the AMS. This is fully developed analog RF layout. So ASIC chip design flow, as I told you, same thing. So coming to the Gnanodaya VLSI, it's a premier institute for the advanced VLSI studies, located in two places. One is in Martali multiplexer, opposite multiplexer Bangalore, and one more is there in the Hyderabad SR Nagar, near SR Nagar Metro, SR Nagar Metro. Okay. So whoever the faculty trained persons are there, those are 50 plus years of experience in the semiconductor domain. Proven track record with scholarship facility will be available. And what are the unique features of this Gnanodaya VLSI means? We'll give 100% placement assistance will be given. Okay. And whatever the curriculum we are developing, industry standard course curriculum is there, and VPN support is given, and low cost and value for money we are giving. Okay, wherever you see VLS is there, healthcare, automotive, telecommunication, consumer electronics, everywhere the VLS is there. Okay, so how we are giving the placement assistance means first we will take the requirement from the client. Okay, we will guide the student preparing the resume and preparing the technical content. Okay, we'll send the resume to the resumes to the client. After shortlisting, we will make the student to attend the interview and written test and interview. After that, we'll announce the results. Okay, so parallelly, like weekly, we are keeping assessments. Okay, after completing one module, we are keeping assessments every week within that 5 days. Whatever the topics we covered in that, we are keeping the assessments. 30 questions each carries 1 month. Immediately, they will give you the results. And placement like technical seminars also, after completing one module, in that module we are keeping the technical seminar will give some concepts, some topics, so that they can improve the communication skills. And and mock interviews also every 15 days will produce the will provide the mock interviews. Whoever the trainers, there will be shuffle. Whoever the trainers present in the Bangalore, they will do the mock interview for the trainers in the Hyderabad. For the Bangalore persons, for the Hyderabad trainers, they will do the mock interview. So, so here, these are the 20 product-based companies, as I told you in the initially. Intel, TSMC, Qualcomm, Nvidia, Broadcom, MediaTek, all those things are product-based companies. These are service-based companies like Capgemini, Tesla, HCL, okay, Chrysemi, Graphene, USD Global, okay, Samsung, Open Silicon, all those apart from this, 1,000 plus service-based companies are available in the Hyderabad, Bangalore, Noida, and India. So eligibility criteria is you should be like BE, BTech in EC Triple E and ME, MTech in VLSI and electronics. Minimum 60% score is there, and good communication skills should be there. Okay. So why? Because like first 3 months we will teach the basics like basic electronics. Analog part means MOSFET, CMOS, okay, and digital electronics, digital, TICL, scripting language, okay, Unix, Linux, okay, Linux HTA, okay, HTA, and DFT. These comes into the basic, okay. After this basic, again, core will come. So if it is a design verification or RTL, then we will teach SV and UVM and some protocols. If it is PD, we will teach the flow planning, placement, all those tool related we will teach. Okay. So we should have like one more time we are revising the concepts related to the basic modules, whatever you studied in the BTech. So training process, first registration, discussing the fee and course training period, preparing with mentor support, conducting the mock interviews, 100% placement assistance. Okay, this is the training process. Okay, in between we will provide the assessments, technical seminars related to aptitude also. After technical related seminars, we will give some topics related to aptitude also. Aptitude also, the trainees should give the training uh, seminar on the aptitude related. Okay, aptitude, logical reasoning, all those things. So these are the top companies for the placement support. So multinational companies. Okay, these are the Intel, Samsung, EDA companies. Okay, and Indian startups, service-based companies. Okay, so these companies will give the placement support. Mm, these are the students who placed our students placed in the some companies like Amar Gopal. He plays in Apex. Ram Babu came Germany. Okay, Sham L&T. Okay, and Reshma HCL. Okay, so these are some our successful students who got placed after getting the training. They successfully placed in different service-based companies and MNC companies. Okay, so basically training methodology and intake if you take. So basically like we have physical design, analog layout, ASIC design, and as well as RTL design is also there. RTL design, RTL and FPGA design is there. Okay, RTL and FPGA design is also there. Okay, so physical design is 6 months. Remaining are 4 months only. Daily like not 1 hour, 2 hours class is there. Okay, 2 hours class will be there. Uh, means after class there will be some practical sessions, lab session will be there. Okay, and a weekend batch 6 hours per week, and number of students intake will take 15 to 20 only. And we have the tools, cadence in our tools, and in the front end also we have Vivado and QuestaSim, Model Sim, and all those tools are there. VPN support will be given, and 15 plus years experience trainers and lab technicians are available. Okay, 100% placement support we will give. Okay, so this is the training methodology. So any queries you can call to this number. Okay, or email, you can email. This is our website, www.gnanodayavlsi.com. Okay, yeah.